Hi, everyone. Our project is on relational multi-agent reinforcement learning for pickup and delivery tasks. Next slide. A quick breakdown on the agenda. First, we're going to talk about the motivation, followed by the related work and methods. And last, we're going to talk about discussion and next steps for the project. Next slide. One more. So what is the motivation? Here you can see a video of an Amazon robotics warehouse. It has a large set of holonomic robots whose task is to pick up and deliver these four-sided bookshelves for humans to be able to pick the products that are needed for an order. In this case, it's this very cute teddy bear. Next slide, please. As an input, we receive a graph and a set of goal and starting locations for each of the agents. The objective is to minimize the sum of travel time for all the agents while determining a set of collision-free paths. This has obvious difficulties in the warehouse setting, as there's these long corridors where collisions that are, it's easy to produce a set of paths which have collisions that are non-recoverable. Next slide, please. In the lifelong multi-agent path planner, the problem is exacerbated, as after every agent reaches its goal location, it receives a new goal location, and this process is repeated indefinitely. So the window of goal locations is changing continuously, and at runtime, just determining one set of them in the closed form solutions is computationally expensive. It's actually been shown to be NP hard. This has all sorts of difficulties associated, but one of them is that temporally the consequences to your actions are really separate. So it's hard it's difficult to assign credit for any given action. And that the set of decisions is a highly correlated set. In a vacuum, any one path would be a decent decision, but oftentimes a set of paths is a pretty poor decision given the constraints in the environment. Next slide. Next, we're going to talk about the related work.
Obviously, this question has been answered in different ways before. There exist different formulations, setup, and environments, but most state-of-the-art multi-agent pathfinding planners still mainly rely on centralized planning, and that does not scale well when you go over a few hundred agents. And such planning approaches may not necessarily be adequate for real-world scenarios. One thing is the complexity of state space, and the other is noise and uncertainty, where the paths sometimes need to be recomputed online, and that could take from seconds to a few minutes, which is not something usable in real-time systems. To that end, what we're doing here is studying two methods that consider fully decentralized policies, and then would like to look into the effect of combining them with relational learning. And now, before getting into more details of relational learning, we'll do a brief overview of the frameworks that we're focused on here. First one is PRIMAL, stands for Pathfinding via Reinforcement and Imitation Multi-Agent Learning. It's under distributed reinforcement learning for multiple agent in shared environment problem domains. And you see the architecture and the RL and IL network here. It not necessarily outperform the other uh, centralized algorithms in different scenarios and environments. But overall, as the state grows, the results of this paper was promising. And then the second one is called MAPPER, and MAPPER stands for Multi-Agent Path Planning with Evolutionary Reinforcement Learning. This is to find effective local planning policies where you have like mixed dynamic environments, and by that it mainly mean dynamic obstacles. But the good thing that they did here, and then as one of their main contribution, is decomposing long range planning problems into easier subtasks with where you have like waypoints, coordinated planning tasks, and you do it with the help of global planner. And then finally, the evolutionary approach goes to gradually eliminating the bad policies. And that really helps with the scalability issues where you have a number of agents growing. So your environment becomes more complicated. And then sometimes and also the variance of gradients that you're using grows exponentially. And then this one happened to be quite more robust. With that said, I'll pass it to the relational learning section.
Our final related work is a paper called Relational Deep Reinforcement Learning by Google DeepMind in 2018. A common issue in current RL literature is low sampling efficiency and the inability to generalize, especially to environments that are similar to those previously seen in training but with minor changes. The core idea behind this paper is that by combining relational learning or inductive logic programming with reinforcement learning, we can generate agents that have a higher ability to generalize to such environments through implicit reasoning. The way they do this is by learning relational state-space representations and relational policy representations that lend themselves to this implicit reasoning rather than relying upon explicitly observing these trajectories played out in the environment during training. It's exactly this generalization that we're hoping to harness and apply to our multi-agent pathfinding system. This paper demonstrates this improved generalization capacity over this toy environment called Box World, in which we have an agent that lives in a grid world setting where the objective is to obtain keys that unlock more locks, that provide the agent with more keys, that unlock more locks, and so on until the agent achieves a gem that results in a positive reward signal. The aspect of this environment that makes it very interesting for relational learning is that each key can unlock more than one box, but only one box is along the correct solution trajectory, meaning that only one box will leave the environment in a solvable state such that the agent can still receive this gem. Any other box that's unlocked outside of this correct box will result in a dead end and an unsolvable environment and no reward signal. This is obviously very difficult for any agent that relies on random exploration such as epsilon greedy Q learning or epsilon Q learning. Because any random step that results, if you rely on randomness, you are more likely to open a non-incorrect box and render the environment unsolvable, and therefore the training time will take much longer and the agent will have a much harder time generalizing, especially further along the solution trajectory. And this is exactly what is observed in the results of this paper. We train each agent on a set of environments with a solution length of 3, meaning that the agent only needs to unlock 3 boxes in order to obtain the gem. And we see from this figure that the zero-shot generalization of our relational agent is far superior to that of the baseline agent, in that when we train on these environments with a solution trajectory of length 3 and then test it on environments with solution trajectories of longer length, we see a much, much higher performance from our relational agent than we do from our baseline agent.
So I'm going to be talking about the mathematical formulation. First, we have state space. So the environment of the warehouse can be represented as a matrix because it is a 2D grid world. All the robots travel um, in a grid-like fashion, as you saw in the previous videos. The warehouse is already storing items in a grid-like fashion. So in the example below, we can see G, where G represents the environment in which the agents move, where P stands for pickup. So the observation space is these 4 channels concatenated together. Now for the action space and transitions, the action space is defined as up, left, down, right, or no action, or wait. There are only 5 actions, as we're not including diagonal movement in the grid world. And the transitions are deterministic, where in the equation, a short path calculates the shortest path from the agent to the goal. So the probability is either 1 or 0, depending if the action is along the shortest path.
So we will be defining a series of rewards that will define how the agents reach the goal. The goal will be obviously the highest value reward, but we will also have a series of negative rewards that will penalize the agents for certain actions. To motivate agents to reach their goals quickly, we want to penalize them at every time step they are not on goal. So that's basically a negative reward for movement, no? And then we also don't want them to just stay on a place, no, which is off the goal. So that's why we assign a higher punishment for that action. With these two previous negative rewards, it could happen that the agents move forward and then backward and move on forward, no, and like they can get stuck in this type of behavior. So we need to also establish an oscillation penalty. And finally, also there's specific scenarios where agents trying to move into the same empty cell can collide, especially when these agents aren't nearby and so they cannot be detected normally. Like normally it's an invalid action to collide with a nearby agent, but in this case they are not seeing each other, so it had happened, and that's why we define a negative reward. And there's obviously no movement on goal, which is when it's on the goal, we don't want any reward, no? So these rewards are certainly, we based ourselves on the other paper, no, that we discussed earlier, no? Because we have the same environment, no? So it's understandable. So this is our warehouse environment. We have a series of agents, we have a series of obstacles, and each of these agents have an objective, no? Which continuously changes when they reach it, no? And it is basically a graphical representation of what could be a warehouse environment, no?
This is the mechanism from the Google DeepMind paper that allows the reinforcement learning agents to perform relational reasoning. Borrowed from transformer networks, we essentially see a multi-headed dot product attention layer here following the feature extractors or the convolutional layer. What this does is it allows the agent to identify entities in its environment, in this box world case, simple pixels on the screen, but by extracting these entities and then learning associations between them in this multi-headed dot product attention layer, we can allow the agent to learn higher order relationships between, of course, identified entities in this environment. And furthermore, by stacking these relational networks or relational layers, we can allow the agent to learn higher and higher order relationships, meaning that if we stack two of these layers, we can have second order relationships and third and fourth and so on. And in doing so, we can allow the agent to generalize and learn generalizations much more effectively. And these are the questions that we're interested in exploring during our research and when we're analyzing our results. First and foremost, we are interested in analyzing how the generalization capacity of our multi-agent pathfinding systems changed. Does this relational reinforcement learning technique indeed improve our generalization capacity? More specifically, what is the zero-shot generalization performance of these agents on new warehouse configurations? For example, if we have a warehouse where we can modify it slightly, for example, closing doors or blocking hallways, or even having similar layouts, similar but different layouts of warehouses, how effectively do these agents generalize with no more training? Similarly, we are also interested in how much the training and inference time increases by adding this relational reinforcement learning module. Of course, computing a multi-headed dot product attention with every training step is an expensive operation, and this will indeed almost guaranteed to improve training and inference time. The question is by how much does this increase, and is this still a computationally effective approach to this problem? Finally, and perhaps the most abstract and most difficult, is this trade-off between A* and reinforcement learning. A*, of course, is exact. It gives an exact answer for any time it's run, but it can be computationally expensive depending on the branching factor of your environment. Whereas reinforcement learning can be less expensive, of course, barring a very large and very complex model. But it's probabilistic. There are cases where reinforcement learning can fail, especially when it's not trained on enough data, or the sampling efficiency is too low, or for any reason. This reinforcement learning approach isn't guaranteed to be exact. How dramatic is this trade-off? Is our relational reinforcement learning agent good enough? Can we train it to the point that it performs well enough that we can accept our lowered computational costs while still achieving good performance?